Hey guys, welcome back to the Turbo V6 YouTube channel. In this episode, we're going to continue reverse engineering the LS1 PCM. So if you haven't already, please go and watch part 1 of this series, and we'll go through how to set up all the software to be able to get started with this episode. One minor point before you go watch that, I did screw up, and you do not actually have to create an account to download the CPU 32 files from PCM hacking, so sorry if you signed up, but hey, maybe you can contribute. I actually have the link in the description below to go have a conversation about these videos. If you need help, there's people that can help, maybe even me. So we'll get to the video. So to start off where we kind of left off last time, we'll open up the project that we started, and basically the disassembly is pretty much complete, at least the auto analysis, and the specific thing that we're going to jump right into is the manifold pressure PID, which we discovered last time by looking up the reference to the PID hexadecimal value 0B, and therefore we found that this memory address is basically the manifold pressure. We'll go with L, and then I don't know if I already labeled this or if I forgot to save it. So that memory address is most likely manifold pressure. And you can see here that it's moving a word. So this is a 2-byte value. So if we jump to this memory address, you can see that it doesn't currently have a size. I think that's what these question marks are kind of indicating, that you don't have a size for this memory location. So if we want to go ahead and hit T, and we can type word, we can just select built-in types. So now that is designated as a word or 2 bytes. And over here you'll see that there's only currently one cross-reference memory address, which is the PID. So we go back to here, yeah, there's only one, reference to this memory location. But like I said, we only did the auto analysis, so there's likely some missing memory locations that are referencing this specific RAM location. So one way similar to how we found this PID is we can go ahead and copy this, the last 4 digits of this memory address, and we can search in memory for all of the locations that contain those bytes, those 2 bytes of that memory address, that memory location. And we can go through and see if we find any that are not disassembled. So obviously this first one is the PID. Going through, there's 1, 2, 3, 4, 5 more. So that one's not disassembled, that one's not disassembled, that one, and that one. So there's basically 5 potential other references to that memory location. And now one trick I found was to find out where to disassemble or start to disassemble this memory. It's actually kind of difficult. I think you can kind of guess and just go in here. There's a hotkey of disassemble, or D. So you go to one of these memory addresses and you just disassemble. It works, but you're missing kind of all of the lead up to that. There's a bunch of code that's likely above that. So the one thing you can do with this window is you can grab here and you can toss it in this pane, and then it'll just become a tab down here. So that will be helpful when jumping between kind of all of these memory addresses. But if we go back, we can Alt left arrow to go back a bunch and find a return. So this is kind of the key that I found to disassembling a whole function. So most likely all of these memory addresses that we found that are calling to the manifold pressure are within a function. And this is basically how you get back from a function. So if I copy this instruction, which is the return, and I go to one of these and I search for this, but I don't want to search all. I just want to find the next. Actually, I want to find the previous. So if I'm here and I find the previous, it finds another return. And if I go to this memory, that's the next instruction, and I disassemble from there, that should be a function. So if I hit the F key to make it a function, now I find that my manifold pressure is referenced right here. So see where this basically disassembled incorrectly because I started disassembling it at this byte as opposed to this byte, which is now giving me the correct operation, which is a move. I forget what the other operation was, but it was incorrect. So I can go and do that at all of these memory addresses. Find previous, disassemble, function. Oh, and that found a couple for me. Go to this one, previous, disassemble, function, and there we go. Now we have all of the memory addresses that look at that manifold pressure that goes into the PID. And yeah. So now we have a bunch of places to look at to see where that manifold pressure comes from. So now we can get rid of this search and we can go to this memory address and we can find, now that we have all of these references, because we disassembled all the code that should reference it. There may be others, but that was a pretty good way to get them. So I can click on this cross-reference and now it will list kind of the same information, but it will tell whether or not it's reading or writing to that memory address. So most likely, and you can see the functions as well. So this right here is a function, the PID, so it's reading that memory address into D0. There's really two that we want to kind of key in on. There's these two writes. So that is where the manifold pressure is getting written to that memory location. So I think the next thing is to look at both of these to see, what's getting put in there. So there's two different functions. You can see that, these are the default function names, 807E0 and 809E4. So those are two separate functions that are writing to this, manifold pressure. So we'll kind of want to understand maybe why there's two different functions that are writing to it, but we may have a difficult time kind of discerning exactly why there's two different functions, but ultimately I think we can figure it out. So let's look at this first function. So here we have D3 writing into manifold pressure. So right above it, it's clearing D3. So there's obviously a default or something that's clearing it, and there's likely a fork. So if we look at the function graph, we can see that right here it's putting D3 in a manifold pressure. And this function portion, it's moving a 1,4FF into D3. Over here, it's comparing to 1,4FF into D3. And over here, it's clearing D3. So that right there is, a minimum because it's clearing it. It's not going, most likely it's not going negative. There's not a whole, bunch of signed values in this PCM. There's a handful, but there's not a ton. So that's most likely zeroing it. And then right here, because it's comparing to the same value and then moving the same value, it's actually probably putting a maximum. So because we actually know that what this value is in, it's actually in KPA because, or most likely in KPA because it's in the PID. If we go back to the PID, it's dividing by a value and then returning. So this value is 51, it's dividing by 51. So if we divide that maximum value by 51, we should see something interesting. So right here, 14FF, which is 5375. So if I take 5375 divided by 51, it is 105, which is an interesting number because by factory, this PCM will not basically output a value of higher than 105 kPa. So that kind of keys in on that this memory address is kPa times 51, basically. So in here, we can put comment. This is kPa times 51. So if I go back, we see that this is the minimum, that's the maximum D3. It's comparing to what's in D3 here. It's comparing to, FFFF. So I don't know why it does this. This is kind of wasting instructions or computation, but it's comparing with the max of 2 bytes or a word, FFFF. And if it's bigger than FFFF, it's comparing a long because it's doing some manipulation of math up here. If it's basically over a word max, it just puts 14FF, which I don't know. I'm not a programmer, so I don't understand exactly why that's the case. But up here, if we keep backtracing to test D3 and it's branching whether or not it's probably finding out if it's a negative number, and then if it's negative, it's basically clearing it. And then up here, it looks like it's taking this is another RAM memory address, FFFFB290, which is just 2 bytes off of 292, I think was this manifold pressure, 296. So it's just slightly up here, 290. So that's another, kind of word, because it's multiplying a word by what's in D3. And then these right here are some calibration parameters. And then it looks like over here it's moving D3 into 290. And then right above it, it's moving another higher RAM address into D3. And then shifting it, basically doing some multiplication and division to it. So yeah, this function kind of starts out with this memory address. So I think that's probably where it comes from. So this might be the raw analog value. So let's look at that. it's another word, so we can go in word. Same thing with this guy. And then this is a word, so it's moving this calibration. So this calibration parameter is also a word. Same thing with this calibration parameter, just to get the types kind of, in line. It's probably not necessary, but it does, make it a little bit easier to read. And then if we want to, we can go in to look at the decompilation of this function, which is a little bit probably more than what we need to look at. But the first couple lines are probably helpful. So it looks like it's taking this word. That's maybe the raw RAM address. Let's look at the cross references. So there's 3 addresses that are reading that, or 3 functions that are reading that address, and no writes, and it's pretty high in the address space. So that's looking like we might have to search for this F2BC to see if there are any other memory addresses that are looking at that. Looks like maybe one here. Let's look for looks like this, disassemble. That's a function. So that's one other function, but it's also reading that memory address. So now we have kind of 4 cross references that are all reading that RAM address. There's nothing writing to that. So yeah, maybe that's the raw analog read of the manifold pressure. So that's this first function that we pretty much looked at. That's this raw manifold pressure, question mark. And then let's look at this other function. So this guy doing similar stuff, looks like moving D3 in a manifold pressure, clearing it, seeing if it's over the 105 kPa. And then look at this, it's looks like it's these are already my words, so these calibration parameters are the same as the other function. B290, that's also that same. Oh, it looks like it's doing the same, pulling in the raw manifold pressure on this function. So yeah, that has 2 functions that are pulling basically the same value and putting it into that manifold pressure memory reference. So yeah, that's yeah, now we have more information and potentially a raw analog value that is read in from the computer. And these calibration parameters, I'll tell you, are what is going to take this raw ADC, like analog to digital conversion value, and put it into a KPA based on, I don't remember what this is, but I've actually previously looked at, open XDFs, and this is basically the offset and KPA per volt, or ADC, bit that converted from a raw ADC, analog to digital value into the KPA value, which obviously, if you're boosted, you want to update this to map, 2-bar map, 3-bar map, etc. So these are previously defined in XDFs, which is another way to kind of trace someone's footsteps, basically. If you find out the memory location for the calibration, you can find out that, oh, okay, this is the map sensor offset. So then you can work backwards from, you know, maybe this memory location for the calibration. You know, that's, you know, this hexadecimal value is going to convert to, you know, the KPA value. And yeah, you can work backwards and, you know, search here for all the different memory addresses that, well, maybe there's another function. So yeah, now that is another location that is calling you know, this calibration for the map sensor. And it looks like, yeah, there's a couple other very, very close values. So like this B292, that's really close to this B290, which was, you know, some other form of manifold pressure. So yeah, hopefully that helps. I don't want to make this too long-winded, so we'll end it there. Thanks for watching. We'll see you later.